All right, let's get started. I imagine everyone is just here for the first slide of the lecture, the results of the Mini Project 1 Kaggle competition. So, as you know, there's both a public leaderboard and a private leaderboard. The private leaderboard is not revealed until about 30 minutes ago. But everyone saw the public leaderboard, so this is what it looked like. We had called Tanner, interesting name, interesting team name. And then the question is, well, which of these teams moved up and moved down the rankings given the private leaderboard? And so here are the results. And Tanner Models is still in first place. If anyone of those team is in the audience, can you stand up? Well, let's give them a round of applause. What about you guys? Okay, stand up. Come on. So I'd like to highlight a few things about this particular competition. We have our biggest overfitters, the Collie crew, who went from 5th place down to 8th place, at least in the top part. And then down here we have, although it's a little bit, things get a little bit more volatile lower down in the rankings, but discounted freeze-dried eggs also dropped 4 slots. So overfitting is something that does happen. And one thing that you do see is the number of entries, right? This is how often you actually query the public leaderboard. So some of you guys are quite active. And the TA got a little creative setting the benchmarks this year. So the best TA benchmark was a little bit challenging to beat because the TA has extensive experience with Kaggle competitions, having played in several of the past few years, even though the TA wasn't officially part of the class. That's Jim. But hope you guys all had fun. Any questions about the competition or the report? Okay, so the report, I should just reiterate, is a fairly standard document. Just document everything you've done. Hopefully it's not something that's meant to be stressful. Just basically document everything you've done, document it well, submit it. Okay, then moving on to the content of the lectures. So the past 2 lectures we've been talking about aspects of unsupervised learning and segueing to things like latent factor models that try to learn these low dimensional representations of the data. And in fact, even in unsupervised learning, the goal is to learn these low dimensional representations of the data. In this lecture, we're going to talk about embeddings, which are, as a broad concept, embeddings are arguably the most widely used form of unsupervised learning, or these sort of representation learning approaches today, particularly those that rely on deep embeddings, which we'll talk about very briefly at the end. But most of this lecture will be sort of more classical embeddings, just so you can build up some of the mathematical intuition, and then taking those ideas and extending the deep embeddings is a relatively straightforward, well, conceptually relatively straightforward process. Of course, there's a lot of details there, but hopefully this lecture will set you up to learn that outside of the class. So in embedding, again, we're doing representation learning. So we're going to learn a representation over data points. So this is at this level of abstraction. It's just like a latent factor model, just like a lot of the things that we've been thinking about. And so in the simplest case, we'll have a matrix, I'll call it U. And every column of U corresponds to the data points. So this notation is a little bit different than the other notations that we've seen. And I should just point out that these notations are fairly fluid in the literature. So you may read a paper that uses one notation and read a different paper that uses a different notation. And the important thing is to not get bogged down in the notations too much, because they tend to be fairly fluid in terms of how they're used, and just to understand sort of what's happening. The thing that's kind of key to an embedding is that there's some notion of semantics encoded in the embedding via some kind of either similarity or dissimilarity metric. So, for example, the distance between 2 points in this embedding may capture some semantics, or their cosine similarity or unnormalized cosine similarity may capture some semantics. And the latter one, actually, as we'll see later on in this lecture, generalizes latent factor models. So one can actually think of embeddings as, in some sense, a generalization of the latent factor model approach that we've seen in the previous lecture. And so I'm going to start off with one of the earliest embedding works. And the purpose of going over this, and I'm going to go over it kind of fast, is simply to show you where this field came from, not necessarily where the field is right now. And so it's not on the homework, so maybe that's a point of thing to keep in mind. So I'm going to go over this fairly quickly, just to give you a sense of where this field came from. And then the rest of the embedding topics in this lecture will be increasingly more modern embeddings. Okay, so the first thing I want to talk about, again, this is a very classical approach that's perhaps not so popular today, is a locally linear embedding. So the basic idea is as follows. We have an unsupervised data set X. We want to learn an embedding of every data point in X such that local linearity is preserved. However, the dimensionality of U is much lower than the dimensionality of X. This is also known as an instance of what's called manifold learning. So for instance, just as a simple example, if this was my data, or this is my data distribution, and this was my training set, unsupervised training set from that distribution, and the color coding here is merely for visualization purposes. They have no other meaning. They're primarily for visualization purposes. Then an embedding of these three-dimensional data points, this two-dimensional data points look like this, where the color codes now help us register the points. So the goal is to learn that U representation given an X representation, given a data sample from X. And, sorry, one more thing. This is a locally linear embedding because locally, for any given point, its neighborhood looks very similar, right? The same points are oriented, modulo some transformation, in the same orientation around me. It's just that globally it looks completely different. And this is, of course, a very toy example, but it illustrates the point. So that's the idea of a locally linear embedding. It's an embedding that's lower dimensional than the ambient dimension of the data that preserves all the local relationships of every point in your training set. So we're going to define the relationship of every data point X to its neighbors, and then find a lower dimensional representation of that data point that preserves this relationship. So it's a two-step process. And so step one, create a neighborhood, and create a relationship of those neighborhoods, of the neighborhood to that point. And so we'll start by defining a nearest neighbor set. So this is something that's a tuning parameter of the algorithm. So you define your nearest neighbors, the 3 nearest neighbors, the 5 nearest neighbors, the 10 nearest neighbors. And the assumption is that the relationship of the data points in the neighborhood of xi is locally linear. If all the data points close to xi are locally linear, then that implies that xi can be written as a convex combination of its neighbors, or a linear combination of its neighbors. Convex is the special case where the coefficients are all non-negative and they sum to 1. But more generally, perhaps just linear. In particular, let's look at this simple example where the x lives in this two-dimensional space, but we can see that there's a one-dimensional manifold that lies in this space that is the data generating distribution. And locally, so let's say this is my xi, and I define a neighborhood of 2, size 2, so I look at my 2 closest neighbors. Then I can approximately write down the location of xi as some linear combination of its 2 neighbors. So in this case, let's say 1/2, 1/2, just to keep it simple. So mathematically what that means is that each xi can be approximately written as some linear combination of its neighbors. We're going to call it a convex combination. So that sums to 1. And so Wij is the weight matrix. So this is what it means to define a locally linear relationship around every data point in my training set. So the Wij are now parameters of my embedding model that I need to estimate. So step 1 is to define this locally linear relationship of every data point with respect to its neighbors. And so for every data point, I, and for every, and we look at the data points in its neighborhood, and we want to learn a Wij such that xi can be represented as a linear combination of its neighbors. And we're going to learn this W via minimizing square loss, so square reconstruction error. And then you can, manipulate this algebraically. This is something that we often do in machine learning to get a different form that might be easier to optimize. We can, do tricks like factorize that out, and then rewrite it in a different way. Now the C matrix is the formula for this in the bottom right. After you collect your training data, you can just pre-construct the C matrix because the x's don't change after you collect your training data. And now I can write it out in this matrix form. And again, I'm going to go over this pretty quickly. The purpose of this is just to give you a sense of where this whole embedding field came from. Yes?
Is assuming convexity just like a regularization kind of thing, or is it actually not possible if you don't assume convexity?
It makes the learning well posed.
Okay.
You'll have to do some other form of regularization to make the learning well posed otherwise.
Okay.
Yeah. Right. Okay, so given this derivation, again, this is just fairly simplistic matrix linear algebra, just applied the right way. You get this minimization problem equals this minimization problem. Okay, if we can solve this problem, then, and suppose we can solve it well, so the squared error here is very low or almost 0, then what that means is every data point xi can be very closely approximated as a convex combination of its neighbors. Okay, so can we learn this W? And we can learn this W by appealing to Lagrange multipliers. This is just a review of Lagrange multipliers. It turns out that by enforcing the W's to sum to 1, it's similar to saying that I force the absolute values, the sum of W, the one norm, the L1 norm of the W's to sum to 1, which defines this constraint set of where the W's can lie on, and therefore, we want to find, this point in the higher dimensional space where the Lagrangian, or where you get the Lagrange multipliers are aligned. Sorry, you get that the tangent of the constraint boundary is in the same direction, modulo multiplicative factor, with the gradient of the loss function. This should be reviewed, at least at a conceptual level. And of course, the solution tends to be in corners. Okay. So we take the gradient. We can write out the Lagrangian. Again, I'm just going to write it out. Take the gradient, solve for it equal to 0, and you can show that each Wij is proportional to that formula. There's nothing very magical going on here. I am going over this a little bit fast. They're, again, just manipulations of Lagrangians and matrix gradients and linear algebra. The implication of this proportionality, so the fact that at the solution, is that when the gradient is 0 goes to Lagrangian, you have this proportionality relationship implies that this is the solution. So now if I can compute this C matrix and invert it, I have the set of C matrices. I have one C matrix per data point, and I can invert it. Then I have I have this closed form formula for the weights. So this is just a way to estimate the local linear relationships of every data point. what's interesting about, what are some interesting properties of this local linear approximation? Well, it's invariant to rotation. So if I have a rotation matrix A, it doesn't change the solution W. It's invariant to scaling. If I scale all my data points by a factor of 5, it doesn't change the W that I estimate. It's invariant to translation. If I translate all the data points, if I shift them all with an additive shift x prime, it doesn't change my relationship. Okay. So the story so far is, for these local linear embeddings, we want to, first define a relationship between every data point and its neighbors. And we define this relationship by estimating a local linear approximation of every data point as a function of its neighbors. And that's what Wij is. Wij is saying, I can write out xi as this linear combination of the neighboring points around xi using this weight, or the linear combination of these weights Wij. Okay, but recall that the goal of learning this embedding is to learn this new representation of every data point. I'll call it U. And for local linear embedding, the goal is to learn such a U that the local linearity property is preserved. And we want this U to be lower dimensional than X. So, okay, what do we do next? So we have this W. We estimated this W from the raw data. And now we say, well, we're going to learn a U that respects this local linear relationship. That means I'm going to hold W fixed. I'm going to throw away the X's. I'm going to learn a U such that UI, the low dimensional embedding representation of data point I, can be approximately written as a linear combination of the low level embedding representation of its neighbors, where the exact relationship Wij was estimated from the raw data. So now the W's are fixed, and I'm going to estimate U. In other words, let's say I looked at some data point here, one of the red data points. I estimated how it should be modeled as a linear combination of its neighbors using the original X data set. Now I'm going to throw away the X's, and I want to learn a representation of that data point. I'll call it U, and I'm going to learn a U for every data point. But for every data point, I want it to be also represented as this exact same linear combination of its neighbors. So I'm going to simultaneously learn all the U's such that it simultaneously tries to approximately satisfy this local linear combination of its neighbors property that was estimated from the original raw data. So now we can write this down as a minimization problem. Because again this problem is non-identifiable. I can scale, I can translate. There's this continuous space of effectively equivalent solutions. I'm going to constrain the sum of U's to be 0, so the translation is centered around 0, because the whole thing is translation invariant otherwise. And because it's scale invariant and rotation invariant, I'm going to force U transpose to be that in. Okay. I'm not going to go over this derivation in detail. This is fairly straightforward applications of matrix linear algebra properties. If you're interested in this line of research, over time you'll become very comfortable doing these types of manipulations to find a form that you can optimize or solve for efficiently. So I think in the interest of time, I'll just skip this. Basically, it turns out that you can use PCA to, after you set up the problem the right way, you can use PCA to solve for U. Just skip to here. So the local linear embedding, which is arguably the first prominent use of embeddings in machine learning. This paper was published, a long time ago. says that I want to, learn of this low-dimensional representation of my data set such that every data point has this local relationship with respect to its neighbors, and that's captured by this W matrix. And I'm going to estimate it first, and then I'm going to try to preserve it as much as possible when I estimate my embeddings. That's the high-level idea. And then you can apply it to this data set, this synthetic data set. This one has 2,000 samples, data points sampled from this distribution uniformly. And then you can choose the size of your neighborhood. So the 3 closest data points, you learn this view, it's not very good. You can choose 6, a neighborhood of size 6. Okay, but not great. And then this is a neighborhood of size 9. So now it looks reasonable, right? Now it seems like with a neighborhood of size 9, I can build a local linear approximation such that I can recover, this 2-dimensional manifold that maps that can map to the implicit 2-dimensional manifold that's living in this 3-dimensional space. So now the U here is 2 dimensions. And every data point here corresponds to the data point there. And all the local relationships are preserved. So it's almost like I've learned how to, take this wrapped sheath in 3-dimensional space and unwrap it and write out a coordinate system just within this 2D plane. And then if you go to higher neighborhoods like 12, you get the same thing. It's because the problem is not identifiable. You can flip the meaning of the axes and you get the exact same solution. So here are the axes. One thing that's interesting is that you see that the stuff on the inside gets mapped to a broader space in U, and the stuff on the outside gets mapped to a narrower space in U. And that's because there's more curvature in the original 3D space. And so the local linear approximation in the original 3D space has some distortionary effects because in 3D space, because it's more curved on the inside, the distances are not exactly comparable to the distances on the outside. Question, yes?
What happens if it's like a sphere where it's continuing on the other side of the map?
The question is, what happens if it's a sphere where it's continuing on the other side? I think that's a problem. So I was like, I think that's okay. No, it's not okay. It'll try its best, but it's gonna learn. But there's a part of it that's gonna look really weird. Part of the embedding that's gonna look really weird. Let me see if that's a correct answer to your question. Yeah, that's what's gonna happen. Now, of course, I could. Well, there are extensions. You can imagine extensions that learn in polar or radial coordinate spaces, rather than have the embedding in Euclidean space. But that's beyond the scope of what we're doing. Okay, so I just really wanted to show this as a warm-up because it was at the time a very interesting idea that sort of captured. Showing that you can learn these embeddings that captures interesting structure of the data, and that it can actually work on on data sets. These days, people learn embeddings on much bigger data sets, and so the bulk of this lecture will be talking about increasingly more modern embeddings that people have developed, and I'll highlight some of the interesting techniques and technical questions that underlie the development of these methods. And to start with, I'm going to talk about probabilistic sequence embeddings. So example number 1 is playlist embedding. So imagine that I have a data set, let's say from Spotify or Pandora, of user-generated playlists. So a bunch of people generate a bunch of playlists of songs, so it's just a sequence of songs. And so each item, each data point now, is a song, or just a song ID, I guess. In this case, let's say there are no features. And we learn an embedding of songs such that such that this embedding has some semantic structure that corresponds to some modeling task that we have. And I'll make this more concrete in a few slides. The second example, which is extremely popular these days, are word embeddings. So people write natural text all the time, which are just sequences of words. Can we learn an embedding or a representation over words that we can, that we use to model word sequences? And again, these will be made concrete in the very next slide. Okay, so here's how you might think about setting up the training problem. We have a training set. So there's a, let's see, how is this set up? So S is the ground set. So it's the set of elements. That's how I'm writing up this notation. So we're going to consider the case where we have no features. We just have the song ID or the word ID. So S is just the set of unique songs or the set of unique words that we're modeling. D is the set of sequences. So they're either the set of documents or a set of playlists. So every P in D is a sequence of songs or words. So each of these PI superscript 1 through N, the value of this PI is one of these S's. That's how this notation works. And the goal is to learn a probabilistic model over sequences. So given that we've observed, and it can get more complicated than this, but just let's say just given that we're conditioning on the previous word or song, what's the probability of observing the next song or word as a function of the training data here? So it looks a lot like logistic regression, for example. So something that we're going to talk about a lot in the next 2 weeks is probabilistic modeling. But I'm just going to give you a small flavor of it to start off with. Although the purpose of this lecture is about embeddings, not about probabilistic modeling, so we're going to talk about this aspect a lot more in the next few weeks. But it's hard to talk about in these probabilistic embeddings without going into a little bit of probability. So here's just a little bit of probability. One way to estimate this probability is to simply have a lookup table. So in essence, we're going to memorize this probability table by having the number of entries equal to the number of ground elements. So if we have 7 words or songs in our ground set, then we have a 7 by 7 or 7 by, you may have a special start node. So the start of a playlist or the start of a document. But effectively 7 by 7 parameter table. So these are the parameters I'm going to estimate. I'm going to estimate this from the data. So condition on observing song S1. What is the probability of the next song? And this is sort of the probabilities, and if they can sort of keep going both horizontally and vertically, because the ground set of songs or words can be huge. And so this is sort of the starting point of thinking about all this. The problem, of course, is that this is huge, right? So the number of parameters we need to estimate from the data is the quadratic in the size of the ground set. And if you want to condition on more than one, so let's say I want to condition on the last 2 songs and then predict a new song, then it's cubic. The number of parameters is actually cubic in the size of the ground set. So this is way too expensive, and this is one of the things that we want to avoid. So one of the ways that we can avoid that is to learn a low-dimensional embedding, so that we can estimate these probabilities very similar to how we estimate logistic regression models, but with a feature that we're going to learn, which is the embedding. And so we're going to talk about it in the context of playlist embeddings and word embeddings, or word-to-vec. And then we'll do a little bit of comparing of the 2 approaches. Okay, First off, Markov embedding. So we're going to talk about Markov models in much greater detail later on in this class, but just again, it's hard to completely sequentially make these things sequentially clean. So I'm going to just talk about it very briefly in this lecture. A Markov embedding works as follows, and this one is going to rely on distance semantics. So let me explain exactly what this model is doing. The probability of observing song S conditioned on currently being at song S prime. So I'm trying to model all possible playlists. I'm going to model that as proportional to exponential of the negative distance between u of s minus v of s prime squared. So u and v are two embeddings that we're going to estimate. So you can think of u sub s as the embedding of the entry point of a song, and you can think of v as the embedding of the exit point of a song in some abstract space. Because of this proportionality argument, we can actually write down the probability exactly by just normalizing by the appropriate normalization constant, which is just the sum of, which is just the same term as the numerator, but summed over all possible songs. Those of you who look at this a little bit carefully will realize that this is exactly a logistic regression model, except the scoring function, except it's multi-class. In logistic regression, there are two classes. There's positive and negative, or 1 or 0. And here, the number of possibilities is equal to the ground set, size of the ground set. And the scoring function is not a linear function. It's this distance function in this embedding space. But otherwise, at a high level, it's a logistic regression function model with some scoring function inside. But the scoring function is not linear. So I call it log radial. It's my own terminology. I'll explain what that means in a second. Okay. So this is the exit point. So now let's imagine we have a 2D embedding space because it's easier to visualize. This is the exit point embedding of song S prime. Every song on this circle whose entry point embedding, so every song whose entry point embedding u sub s double prime on this circle, because it's equidistant to v sub s prime, they have an equal probability of being transitioned to, by definition of this formula. So this is essentially what's happening, right? We're going to learn this embedding space where we have an exit point and an entry point representation of every song in this embedding space, such that, based off the playlist that we observe, the empirical distribution of playlists that we observe, we want to learn this low-dimensional embedding such that the conditional probabilities line up with the empirically observed conditional probabilities. The reason why we want to do this is that if we have a k-dimensional embedding, or in this example k equals 2, we're learning 2 times k parameters per song, which means 2 times the size of the ground set times k parameters total, which is much smaller than the size of the ground set squared. If the size of the ground set is like 100,000 songs, then that whole probability table that I talked about before will be 100,000 squared, or 10 to the 10. Whereas if k equals, let's say, 2, in this simple example, then this is simply 400,000, 4 times 10 to the 5. Just orders of magnitude fewer parameters. Okay, so again, there's some notion of probabilistic reconstruction here, right? So we're basically saying we have this data set of playlists or sequences of songs or words, and I want to learn a low-dimensional representation, or in this case, a pair of low-dimensional representations for every song. such that under this particular probabilistic model, which is a logistic regression model of the sequence, I can I have a probabilistic notion of reconstructing these playlists. Any questions? Okay, so the learning goal is maximum likelihood. So given the set of playlists or the set of documents, I'm going to maximize. I want to learn a model, this embedding model that maximizes their joint probability, and things factorize as so, because we're assuming that things are condition dependent given the current token. And so this is the learning goal. Like always, we're going to take the negative log of this objective. So rather than maximizing the likelihood, we're going to minimize the negative log loss of this probabilistic model. And we'll solve using gradient descent, or stochastic gradient descent. There is, you might ask, this normalization constant is very expensive. In normal logistic regression, it's very trivial to compute because there's only two choices. In multi-class logistic regression, this normalization constant is actually very expensive to compute, and there's some heuristics to approximate this normalization constant, but I won't go into it. So that's the story so far. We have training set of playlists, we're going to build probability tables, and one of the things that's perhaps kind of interesting is that there may be missing values, or it may be hard to generalize directly, and when we have this low-dimensional representation, then we can actually share statistical strength between songs. So, for example, just like how in the Netflix problem, not every user rates every item, but somehow we assume that there's low-dimensional variability, so we can share information between them by learning these feature representations of users and items. And in the Netflix problem, the scoring functions is dot product between the users and the items. Here we're saying we're going to learn these feature representations of songs, and the scoring function is the negative square distance, and then I'm going to put that scoring function into a logistic regression model. And of course, you can do simple ones. You can do. You don't have to do this dual point model where you have a separate entry and exit point for every song. All this does make the modeling much easier, much more accurate. Excuse me. You can also do a single point model where every song only has a single embedding point. You can do this as well. And then you can visualize, the embedding, right? So here is a 2D visualization of the embedding. This was trained on Last.fm? No. I forget. If you're interested in the details, you can read this paper. I believe this is trained on the Last.fm data set. Don't quote me on that. And then and then you have these embeddings of playlist of songs, you're given this set of playlists of songs. You train this probabilistic model that just tries to predict the next song given the current song, and you learn this low-dimensional representation of songs such that their negative square distance as a scoring function for the logistic regression explains the playlist in terms of negative log loss. And now you can visualize, and you can see that even though we had no idea who the song names, we had no idea who wrote the songs, we had no idea of any of those things, just with the song IDs and playlists, that's the only information we have, we can learn an embedding that actually who preserves interesting semantics, like for example, Bob Marley's down here, Lady Gaga's in the middle, the Rolling Stones are blue. Now this particular visualization is probably not too surprising. People tend to make playlists of just a single artist. This is very common. And so if you're currently playing a song by a certain artist, fairly high probability the next song you play is by the same artist. And so their embeddings of those songs will probably clump together because the closer they are, the more likely they are to be predicted next. Question, yes?
Does that mean if you're in a cluster, it's unlikely that you would go to a song outside of a specific cluster? Like,
Right, according to this model, yes. The probability, because it's exponentiated, right? So the probability that you would jump to a song far away decreases exponentially with the square distance under this particular model. So, right, so you set out you have to define a semantic interpretation of what the embedding means. Like in the local linear one that we just talked about very briefly, we say what this embedding means is that local linear relations are preserved with respect to the raw features. In this embedding, I'm saying the probability of jumping to another song as measured as it decays exponentially fast as I get further away in this embedding, and then I'm going to fit this embedding to the data under this semantic. Right. So there's a little of a cat and mouse game where you define the semantic, and then you fit the embedding. You can't, otherwise you can't. The embedding has no meaning, right? And it's just this abstract space. It itself has no meaning, so you have to define it as semantic, and then you can fit it to data. And so the semantic is exactly defined here. Given this semantic, you can fit it to data, because now you can minimize log loss of this model. You can sample new playlists. So for example, if you train this model and you generate, given the current playlist, partial playlist, you can generate the next song by just sampling according to one of these models. The probability you choose the next model is exactly this probability. Of course, in this particular case, we train this embedding using no attributes of songs, and only their presence or absence and position in various playlists. What if we added a brand new song, in which case no playlist has ever been created for this brand new song? This is similar to like if I added a new movie to the Netflix problem and no user has ever rated it. What do you do? This is also known as the cold start problem in these kind of representation learning problems. So the answer, is to use some sort of features or attributes that come with the song. So for example, for these music recommender systems, the songs usually have tags like category, artist, and so on and so forth. So you can treat them as features. And then there's the question of, well, how do we actually leverage these features to help us train better embeddings? There's a few different options. The authors of this particular paper chose one option. And as I go through a few different examples of different applications, I'll show you a range of different options. In this particular application, they chose to learn an embedding over tags as well. So now we have tags. So tags include things like the genre, possibly the artist, and any other attributes that come with the song. The song has a bunch of metadata. And so the only thing that I'll say here is that the only thing that changed is this part down here, which basically says that I want the embedding of the song to be close to the average embedding of its tags that it's associated with. And I'm going to also estimate the embeddings of the tags. So the A's here are embeddings of the tags or the attributes of the songs. And so I'm going to take their average, and that should be close to the embedding of the song. And now you can visualize the embeddings of the tags. So here are the embedding locations of the tags. So hip hop's over here, rap, R&B. So tags that probably have similar semantics are located similarly in this embedding space. And now if you have a brand new song, and no user has ever added this new song to a playlist, if this new song has tags, then we can initialize the embedding of this new song as the average of the embeddings of its tags. And then as we collect data about how users add this song to playlist, we can re-estimate the embedding. And you know, I don't want to get too deep into it, but that's actually implied from the probabilistic interpretation of the objective function. Okay, so now I'm going to switch gears to probably the most important part of this lecture, which is word embeddings. So now we're given a large textual corpus, let's say Wikipedia or Google News or the New York Times or what have you, hopefully not Reddit, but sometimes Reddit. I'm going to learn a word embedding to model sequences of words. Sorry, if you guys know about the learning word embeddings these days, Reddit is actually one of the most popular corpora, and it's highly problematic because of all the toxicity on Reddit. Okay, we're going to learn a word embedding to model sequences of words that exist in these textual corpora. Okay, and now I'm going to switch gears on the semantics. So for the song playlists, we use distances to capture semantics. Now we're going to use inner products to capture semantics. So S, I'm going to keep the notation the same for now. And so S is a word. And given the current word, under this particular simple model, the probability of observing the next word is this logistic model, but the scoring function is now a linear dot product where I have to estimate U and V. And this is basically a lean factor model that we've seen before. Right, so how do you interpret this, what's happening here? So basically, you know, if your current word exit point is V sub S prime, then you know this projection basically projects different other vectors onto this green line at different levels of magnitude. And so that's illustrated by those dashed lines. So the blue vectors project onto a similar magnitude to the green line, and the red vectors project onto a similar magnitude to the green line, and those are equally likely. And so we get this big data set of sequences of words, and we're going to train this embedding such that the probabilities line up with the empirical probabilities we observe in the training set. But now the semantics of this embedding are via this dot product or inner product semantic rather than a distance semantic. Okay, so if I were just to take everything that we've talked about for the song playlist embedding problem and just map it to here with this one change, it would just look like this. Nothing has changed except the ground set are words, the sequences are, let's say, sentences, and the probabilistic model uses this inner product semantic rather than a distance semantic. That is not actually what the word-to-vec model does. The actual word-to-vec model uses something a little bit different. So they use what's called a skip-gram model. And it's kind of an interesting model, right? So what they basically are trying to do is they're trying to predict the tokens of a neighborhood, both before and after. So given the current word, I want to be able to predict the probability of observing any word within a window of the current word, so both before and after. This is called the skip-gram model. Again, this is just the thing I want to model. This is just the thing I want my embedding to capture. I want my embedding to capture the ability to predict words in a neighborhood around me. And the more likely a word is to be in a neighborhood around me, the closer the inner product, the bigger the inner product should be. Keep in mind that everything's inside an exponent, so this inner product can be negative. Right? So what are some benefits of the skip-graph model? So surely the people who invented word2vec considered the standard, one step look ahead kind of probabilistic model. Why might they have chosen the skip-graph model instead? It was a deliberate choice on their part. So here's some intuition about why you might want to choose a skip-graph model. There are 3 sentences. Let's say we consider these 3 sentences. The dog jumped over the fence. My dog ate my homework. Horrible sentence. And I walked my dog up to the fence. So in this particular case, if this was the corpus of text, if this representative of the corpus of text that we want to model, we might think that dog and fence have some kind of relationship to each other, because they sort of appear close to each other often. Maybe not right next to each other, but they seem to appear close to each other. And so the skip-graph model allows us to capture that. And most importantly, it allows us to capture all of it in a single model. So we learn a single embedding that tries to simultaneously predict every word in this neighborhood. Again, we can talk about the dimensionality of the embeddings. If the embeddings are too large, high dimensional, then you can basically do memorization. If the embeddings are too small, then it may not be able to predict well, so your log loss could be very high. And in general, you want to choose a K that's sort of a little bit large, but not too large, because you don't want to overfit. One thing that's kind of interesting about this word2vec model is that you can sort of do some interesting algebra in this model. So for example, this is I don't remember the Czech Republic uses euros now, but at least in this data set they use the koruna. And so you could take the embedding of Czech, a country, plus the embedding for a currency, and you look up the closest embedding point that corresponds to an actual word, and you get back to koruna. And you can do this with a bunch of different examples. These are a little bit cherry-picked, of course, but it's surprising how often you get these interesting meanings. For example, Vietnam plus capital, you get Hanoi, Ho Chi Minh City as the top 2 results. German plus airline, you get airline Lufthansa as a compound word. That's considered a single compound word in this data set. This one perhaps a little bit off. This is Russia plus river. Russian plus river, the closest embedding point is Moscow. The second closest is the Volga River, so on and so forth. You can do more complicated arithmetic in this embedding space. So for example, if you take the embedding location that corresponds to France, minus the embedding location that corresponds to Paris, plus the embedding location that corresponds to Italy, and you look up the closest embedding point that corresponds to a real word, and you get the embedding for Rome. Question, yes?
How come yours more with addition and subtraction? What happened to the multiplication?
I don't think multiplication works very well. In fact, it's not entirely clear to me, personally, why addition and subtraction work that well.
We're not sure about the theory and why this works.
To the best of my knowledge, and this is a fast-moving field, I should mention this is a fast-moving field, and I have not kept completely up to date on it. To the best of my knowledge, there is not a good theory to explain what's happening. This is an empirical observation. And you can do other things, right? You could take a bunch of countries and a bunch of capitals corresponding to those countries, and you could look at a 2D projection of their embedding locations, and you can see this nice relationship. So this like, you know, the same direction added to direction vector added to country gets you pretty much most of the time, not always, to their corresponding capital. Okay, so other than that those cool visualizations, which are very cool actually, one of the things that people use these embeddings for are as features. So in the beginning of lecture, we talked about bag of words representations. No one uses bag of words representations these days. Everyone uses word embeddings these days as feature representations of textual documents, of text. Everything else I said in lecture 1 still holds, but no one uses bag of words representations. Training, again, you train using gradient descent or stochastic gradient descent. You take a sequence. So this is just a learning objective, minimizing log loss. Again, you have some data set of sequences. You have a token, you loop through every token in each sequence, and you look at the neighborhood of tokens around that token, and you minimize the log loss of the probability of observing that token in the neighborhood of the current token. So it's very standard given everything we've seen so far. We're just going to solve this using gradient descent or stochastic gradient descent. Like in the song embeddings, this denominator is very expensive. You have to loop over all possible words. And let's say the number of words is like 4 million, 5 million. So computing this gradient requires a for loop over 5 million things, let's say. That's very expensive. The same thing was true in the song playlist embedding problem as well. I just sort of glossed over it. So I'm going to take a little bit of time and talk about how you might solve for this type of denominator efficiently. So there's many ways you can do this, and they all come with various trade-offs. This is the way that the people who originally proposed word2vec chose to do this. They're gonna propose a hierarchy of embeddings, and so the leaf nodes of this hierarchical tree of embeddings, tree hierarchy of embeddings, the leaf nodes are the actual token ground elements. In this case, the words. So how am I going to write this? So the probability of observing song S1. Sorry. The probability of observing song S1 given song S prime now can be written as the probability of, so I'm going to start, I'll start with the root node. So the probability of, so song S1 is over here. So it's the probability of transitioning from node A to node B, conditioned on S prime, times the probability of transitioning from node B to node S1, conditioned on S prime. And so that's how we're gonna write out this probability. So all I've done here is I've taken this probability formula and I've written it down in this form. And now each of these can be written down as a binary logistic regression problem. Now this should look very familiar to you, except we're learning both U and V. We're learning the features. We're doing this feature learning of both U and V. But this should look very familiar to you as a binary logistic regression problem, rather than this multi-way logistic regression problem. So basically, in order to do this logistic regression, I need to be able to estimate. Embeddings of the inner nodes. So these virtual inner nodes have embeddings, are associated with them embeddings. So I need to estimate more embedding points. But this allows me to compute this probability as a product of binary logistic regression probabilities, rather than this multi-way logistic regression where the denominator is really expensive. So in return for computational efficiency, I need to estimate more parameters. So I lose on statistical efficiency. And in fact, this is a thing that happens a lot in machine learning and statistical modeling, where some methods that are more computationally efficient tend to be statistically less efficient, or vice versa. Because I have more parameters in this model, you might expect that I need more data to estimate it reliably. That's what I mean by statistical efficiency. All right, so the complexity of computing this guy is log of the number of ground words. Right, so before, if I wanted to compute this probability, I needed to, the denominator had to for loop over every ground element, every unique word, which is linear in the size of the ground set. With this type of model, computing this guy, actually just doing the computation, requires only logarithmic in the size of the ground set. But I need to estimate more parameters, because I need to estimate the embeddings of those virtual nodes in that tree hierarchy. So it's statistically less efficient. It needs more data to estimate reliably. But I can train this as gradient descent as before, and it turns out this trick, this reparameterization trick, leads to substantial computational savings. And the data set is huge, so they were okay with it. Statistical efficiency was not a concern. Yep, so just to summarize, every word corresponds to one exit point, and there's some path along the entry points, and everything else is unchanged, and we train using gradient descent. So I want to maybe take a slight step back and talk about the semantics of these two embeddings. In these two case studies, we looked at word embeddings, which are extremely popular right now in the industry, and song embeddings. And the reason why I chose them was because the way that the people who developed these methods developed them is that they made modeling choices that endowed different semantics onto these embeddings. In the word embedding case, they use inner product semantics as the way to endow structure onto this embedding, which is, by the way, extremely similar to the Netflix problem. In the playlist embedding case, the authors use distance as a way of endowing semantics into this embedding. What that means is that when you visualize what's going on, the visualizations tend to be different, right? So, the distance-based semantic means that similar things tend to be clustered together, whereas the inner product-based embedding means that similar things tend to be pointing in the same direction. So when you visualize them, you have to be aware that they have different interpretations. Any questions? Yes.
Is it possible to take a Bayesian perspective and posit priors for U and V?
Absolutely.
Do you gain anything from that, the computation? Like, can you do Markov chain Monte Carlo on that, or?
The data sets are so huge that most Bayesian methods give you a really sharp peaked posterior that you might as well just do a point estimate. So, well, I've not done an exhaustive study, so I don't know how true what I just said is. But in my anecdotal experience, that has been true almost all the time for these large data sets. But I have not done a comprehensive study, so maybe I shouldn't say that so forcefully. But the data sets are so huge that the posterior tends to be so peaked that you might as well just do it once. For the moment. That would be my default recommendation. There may be special cases where that's not true. Okay, so for the last 10 or 15 minutes, I'm going to go over one application of embeddings or extension of embeddings that uses deep learning. This is an example. This is one thing that I teased in one of the previous lectures. I'm going to spend about 10 minutes talking about it in a little bit greater detail. This is I lifted some slides from Julian Macaulay, who was the senior author, or one of the senior authors on this paper, Learning Visual Clothing Style Using Some Learning Signal, which they call heterogeneous dyadic co-occurrences, which is just a fancy name of saying we're going to build an embedding with some semantic meaning. So in particular, they want to learn an embedding where clothes that look visually compatible are close to each other, and clothes that look visually incompatible are far away from each other in this embedding. That's the idea. The training data, so I briefly mentioned this before, a ground set of items scraped from Amazon, about 1 million items. The attributes of the items are the images. So you have an image of the item. And then you also have categories, like coat, belt, pants, sock, etc. So these are all things that you can easily scrape from Amazon. And then you have this particular pairwise relationship that you can also scrape from Amazon. Frequently bought together. Everyone who's ever visited Amazon knows that there's this pane of recommendation saying people who buy this item also often buy these other items. So that's the learning signal. So here's the training goal. Let's see. Theta are the model parameters. Phi is a neural net that maps images to some embedding space. So it maps the raw pixels through some sequence of nonlinear transformations to a k-dimensional space. So the output of this neural net is k-dimensional. D is the set of compatible pairs, and the first loss function says that if these two if a pair of visually compatible items, if their embeddings are too far apart, I incur a high loss. And I'll walk through the formula later. And then D tilde, is that tilde? Yeah, D tilde is the set of incompatible pairs. So pairs of items that are not compatible with each other. And then L minus is a loss function that says, well, if the embeddings of these two items are too close, then I incur a high loss. And furthermore, this only loops over pairs in different categories. I don't care, because you want to find the socks that match with pants, not the socks that match with socks. At least that was the purpose of this particular project. Okay, so the embedding was designed using convolutional neural nets. We talked about convolutional neural nets. For image classification, the final layer of a convolutional neural net is this logistic regression. We're just going to output, some number of. We're just going to treat the last hidden layer as the embedding, basically. We're going to throw away the logistic regression at the top and just have the last hidden layer as the embedding. So in this particular case, it's 4096. It doesn't have to be 4096. It's usually much lower. In fact, this embedding, they call this the Siamese convolutional neural network. the reason why they call it a Siamese convolutional neural network is that you have a pair of images, and you have a loss function depending on whether or not they're similar or dissimilar. And then you produce this embedding, which is just the last hidden layer of the neural net. And then we're going to measure the distance of those, of the embedding points of the last hidden layer. And they should be close if they're visually compatible. They should be far if they're visually incompatible. The loss function captures that. And then it sends a loss function, so through backpropagation chain rule, down both networks, which are the exact same network. They have the exact same parameters. They're just clones of each other. And therefore, they call it a Siamese convolutional neural network, like Siamese twins. Same model. Okay, so that's the idea. Let's just see. Actually, so I actually didn't even, sorry, in my slides, I don't actually have a formal definition of L plus and L minus, but you can look at the paper for details. But intuitively, they capture what I just described. Any questions? Yes?
So phi is the same network in both cases, but
Correct.
they're technically like independent problems, right? Because they're coming from, you're pulling the data from two different sets, in some sense.
The x's are sampled in some way.
Mm-hmm.
The mapping from x to phi of x
Mm-hmm.
uses the same function mapping.
Okay.
Yeah.
But so if I were to look at phi after the training's all done, would I maybe find that there's like two kind of like different modular networks in there based on like the sparsity?
You might. So there's nothing in here that controls exactly what phi is learning internally. All it says is, I want this loss function to be minimized. So that might be true. Of course, visualizing what's happening inside of neural net is an ongoing endeavor. Okay, so unlike the traditional convolutional neural net, which has 4,096 hidden layers in the final hidden layer, they use something much smaller, like 128. So in this case, we're going to map images to a 128-dimensional embedding. Furthermore, you may notice that we don't actually have training data for the negative pairs. Amazon doesn't have a recommendation that says, if you buy this, please don't buy this. Right? Amazon doesn't have that as a training, as something that you can actually scrape. So something that often happens in these types of modeling frameworks is what are called weak negatives. So my default, because there's a million items, the default is that two items are not visually compatible. Only a small subset of items are visually compatible with each other. So my default is that unless I see an explicit signal that two items are visually compatible, I'm just going to assume that they're visually incompatible. I may put less weight on that. So that's a weak. That's what's called in machine learning a weak label, where it's like it's a label that I can basically assume is mostly true most of the time. But it's probably not true all the time. But I don't have a way of actually getting the clean label. But since it's true most of the time, I'm going to assume that it's true. I'm just going to put less emphasis on it. And so there's a procedure to just subsample random pairs of items and pretend that they're just incompatible, and that's what they do. And this is a very common thing that happens in many aspects of this type of embedding learning within machine learning. So for example, people learn embeddings of drugs and chemicals and proteins, right? And you want to know if a certain drug interacts with a certain antigen, right? The default answer is no. And you may have done an explicit test to show that this particular antibody binds with this antigen, but the default is no. That's a weak negative label. So this happens in all data sets where people try to learn these embeddings. You may want to learn an embedding over neurons. You want to know if two neurons encode some behavior. The default is no, because there's so many behaviors and activities, and then you may then receive explicit positive signal. The answer might be yes. Okay, so we train this embedding, we can visualize. This is a slide I showed at the end of the previous lecture. This is a t-SNE, or a 2D projection of the 128-dimensional embedding. And because because the loss function is measured from the distance, so the two embeddings should be close to each other, they're visually similar, you hope to see that the items that are clumped similar to each other in this embedding are indeed visually similar. Yes, question?
Did you train on 128 features and then do dimensionality reduction, or directly train on 2 features and directly view?
Oh no, you want to train on 128. This is a this is called a T-SNE visualization, T-SNE, which is a nonlinear projection of a high-dimensional data set down to 2 dimensions. It's not a linear projection. So you definitely want to train in 128 dimensions and then do this nonlinear projection later. Okay, and then you can do other things, like we can suggest outfits. So because we've learned this mapping from images to this embedding space, you can get a brand new piece of clothing, let's say this red t-shirt, and I just map it to this embedding space, and then I can suggest outfits in other clothing categories that, the model in the embedding space thinks are visually compatible. Okay, so just to summarize, we covered a lot of territory in this lecture, and I apologize for the amount of content, but I thought it was important to get through all of it. The idea behind embeddings is that we have this training data. Sometimes we have labels, sometimes we don't, but we care about some property of the training data. It could be supervised, it could be unsupervised. At this point, when people train embeddings, the distinction between supervised learning and unsupervised learning is completely blurred. You have a bunch of properties of the data, whether it be the local linearity property, or some Markov embedding of sequences, or affinity to be purchased together, or whatever. There's some property. You want to encode that property in some semantic of the embedding, whether it be, which corresponds to some geometric property of the embedding, whether that be inner product or distance. Those are the two common ones. And then given that, given those two things, and given a large data set, you just fit using gradient descent. And one of the things that's very neat is that these days you can use these embeddings as a tool for learning features, learning representations. So in the past, people used to handcraft representations, and now you can just learn them automatically, or learn features automatically via embedding learning. So as I mentioned before, Word2Vec and nowadays more modern versions of Word embeddings that have succeeded Word2Vec are the dominant way that people design features for text modeling. And it has transformed the natural language processing community, and it's actually used in Google search. So when you search for stuff on Google, they use a word embedding to process your query. Any questions? Okay, so there's a little bit of a shuffle in the next schedule for next week. Next Tuesday, I'll be talking about probabilistic models and naive Bayes. That's shifted up from next Thursday. And I was going to talk about recent topics in machine learning, but I'm going to cancel class because the emerging neuroscience symposium is happening all day next Thursday in this room. And so class on Thursday is canceled, and if you're interested and you want to come, you should check out some of the talks. And then recitation on probability, if you want a refresher on probability, is next Thursday evening. That's it.